is VDD. So positive VDD. So the voltage across diode is going to be VD, which is basically anode voltage minus cathode voltage, which is V anode minus V cathode is connected to ground. So which is 0, which is simply the anode voltage. Which is for practical standard diode that we are talking about. What is the voltage drop across the diode that we consider? Standard voltage drop? 0.7. 0.7, which is 0.7. And we get this 0.7 volt. We write this 0.7 volt because we are considering constant drop, constant voltage drop diode model. Okay, so that's how we just write VD equals simply 0.7. Again, we can find VD using Shockley's equation. Shockley's diode model. Shockley's diode model, we have a relationship between ID, which ID is basically the current flowing through this diode. We denote it with ID. This ID is going to be I sub S e to the V T over Vt minus 1. Okay? And usually this term is relatively very large compared to 1. So you can just approximate it with I sub S e to the Vd over Vt. And at standard temperature, Vt is 0.025 millivolt. In other words, I'm sorry, 0.025 volt. In other words, 25 millivolt. At standard temperature. This is the thermal voltage. We went over this in our last course. So this whole process, guys, we did not consider any AC signal. We supplied battery voltage, constant battery voltage. We supplied constant battery voltage, and we found ID and VD. Now, ID is simply because we consider constant voltage drop model. ID is simply VDD minus VD over R. So this voltage drop here is VD. So this voltage minus this voltage divided by R is going to be the voltage across. Is going to be the current flowing through this resistance R. And because this resistance and this diode are connected in series, therefore you will have same current. ID is going to be flowing through R as well. Okay, so we found ID, we found VD. So which means that we are able to solve this circuit using this DC voltage source. And this part is called DC biasing. This part is called DC. This part is called DC biasing. DC biasing means that we do not consider any AC signal applied to the circuit. Is that clear, guys? We simply do not consider applying any AC signal to this circuit. So this is basically DC biasing. So we found ID and VD. ID which is the current flowing through this diode, and VD which is the voltage rectifier. Now, once you find this DC biasing, this diode is basically a nonlinear device. diode is basically a nonlinear device where x-axis is VD and y-axis is I. Now, after DC biasing, we get some point. After DC biasing, we went to this load line in our class. So this is load line. Okay, and this is the diode characteristics line. And this is the point, basically approximately 0.7 volt, and you will have some current, which you can find using Shortleys equation. Okay, so you get this point. Now, the most important thing is this point is called operating point or Q point. Operating point, or people call it Q point. Because this diode is a nonlinear device, and we would be applying very, very small signal to this diode. We would be working with very, very small signal, which could be AC, or it could be noise. It has to deal with noise as well. Okay, high frequency component. Because this diode is a nonlinear device, and in this nonlinear relationship, we will not be able to analyze the circuit. So what we do, we basically apply Taylor series. You probably heard about Taylor series in your, grade 12 or grade 11. Taylor series like 1 plus 1 over factorial to df over dx, right? Then the difference and so on, higher order terms. So you actually discard higher order terms and you keep the linear term. So you keep the first term and the second term to make it linear around, to make it linear around this operating point. So around this operating point, the behavior has to be linear. So this is a straight line. Behavior has to be linear. This is a straight line. So we first find the operating point using DC biasing. We do not consider AC. Now we will apply. Small voltage. We will apply small sinusoidal signal. We call it VD. Small sinusoidal signal. So we are actually superimposing some very, very small signal, and the amplitude has to be, magnitude of the amplitude has to be, what was the number? In our last class I mentioned, it is 5 millivolt, less than 5 millivolt. Magnitude of this VD is going to be less than 5 millivolt. And we have this DC voltage. And throughout this course, it is my notation that the total voltage, the total DC plus this AC component, I am going to denote it with this plus minus. And this actually includes lowercase b and uppercase s. So which means that it has DC plus AC. So it is basically VDD plus V lowercase d. Okay? So I'm going to denote it like that. So now, once we apply these two voltage sources, then we will have some change in VD and we will have some change in ID. And we saw that ID is going to be I sub d plus lowercase id, and then look guys, this equation becomes I sub d t equals id plus id over vt times v sub d. Okay, so now this v sub dt is the small signal, and you have this id over vt. What we can do, we can actually write ID, which is the DC current, plus we can write VD over, can we write VT over ID? We can write it to get the same expression, right? To get ID over VT, we can write it VD over VT over ID. So we get the same thing. The reason I said that is this is voltage, and you can think of this as resistance. So this is your RD. This resistance is basically VT over, I'm sorry. There is a mistake here. It is going to be ID. I'm going to use red color. This is going to be ID, guys. Okay? So it is VT over ID. So this resistance, this small signal resistance is present in this diode. So this diode will have, like, you don't just think this diode itself, there is a small resistance connected to this. So this is RD. Okay? And we need this RD in the next example. We will use this RD in the next example. So now, we now know how to model this diode using small signal. So we apply small signal. So therefore, we see the small signal resistance is present, and small signal current is also present. So if we apply small signal voltage, so small signal current is present. ID, which is VD over RD, which is VD over V lowercase d over VT over ID. Okay, so this small signal resistance is present, and small signal current is going to be there as well. Okay, so therefore, on top of ID, you will have a small signal current, which I denoted with lowercase I, lowercase d. So let's go through this example. Now it is going to be crystal clear. Go through this example. Okay. Again, so you will see throughout this course, I denote V plus to denote that there is a voltage source here, and that voltage source, you can just think of this as positive, negative, like that. So this is going to be V plus. So in short, people write it like that, okay? Because it's an advanced course. So in DC and AC circuits preliminary course, we write the voltage sources specifically, but to actually make things clear for clarity, we just omit this sort of notation and we write V plus right there. So consider the circuit shown to the right with R equals 10K. So you have 10K resistance here. The power supply V plus has a DC value of 10 volt. So V plus has a DC value of 10 volt. Okay? On which is superimposed 60 Hertz sinusoid of 1 volt peak amplitude, which means that you have a DC VDD, which is V plus equals 10 volt, and then we have a small signal VDT, and this small signal is 60 Hertz sinusoid of 1 volt peak amplitude. How do you write it then? VDT is going to be 1 volt peak amplitude. So 1, and it's a sinusoidal signal. Sine, and then omega t. Omega equals 2 pi f, which is 2 pi. F is the physical frequency, which is times 60, 2 pi f t as a function of time. So you have this voltage sources. Now you take the resistance R, and you have this diode. And you take the voltage across this diode. VD. Okay? So this is the source now. The total source is going to be identified with V sub S, T, which is basically positive, negative, this. Did you guys understand, guys? You understood? Raise your hand if you have any confusion, please. Okay. Now calculate both DC voltage of the diode and amplitude of the sine wave signal appearing across it. So because of this small signal, there should be a small signal across diode as well. Small voltage, small signal voltage across diode. Assume diode to have 0.7 volt drop at 1 milliampere current.
You don't have any scheduled reminders due for that.
All right. Solution. First, DC biasing, because we need to find what is the voltage across it. So we have step 1. You go through DC biasing first. Assume no small signal. If there is no small signal, VD is easy.
Just 10 minus 0.7.
Yes. So it is VD is 0.7 volt, and ID is going to be simply VDD. Actually, we have V plus. V plus minus 0.7 over, how much is R, guys? 10, which is 10 times 10 to the 3. How much is it, guys? So it is 10 volt, right? V plus is 10 volt DC. So 10 minus 0.7 over 10,000. And it is going to be, how much is it, guys? In terms of milliampere? 0.
Point 94 milliamp.
94 million. Millions, okay. 0.94 million. So we now know the operating point. Key point here is VD, ID equals 0.7 and 0.7 volt. Don't forget the unit, and 0.94 milliampere. Okay, 93, hold it. 0.93 milliampere. Okay, so this is the operating, yes.
Wait, but didn't the problem statement say that it was 0.7 volts and it had 1 ampere?
Okay.
At the bottom?
Yeah. It says at the bottom, it says that assume diode to have This is the specification. So at 1 milliampere current, you will see the diode will have 0.7. So if current flowing through the diode is 1 milliampere, so it is going to be 0.7. And if the current is even more, it is going to be exponential. You don't see much changes in the voltage. Okay? So it is the specification. At 1 milliampere current, it is 0.7. Okay? So some current has to flow through it because of forward bias. Okay? So now we have VD and ID for this circuit. For this circuit, you will have VD and ID because you apply external DC voltage source. Now, we are going to apply small signal. So therefore, if we apply small signal and you know that current is flowing, therefore small resistance is going to be present here. So we now apply small signal, which is VD key, and we will have this resistance, and therefore a small resistance RD is going to be present. And this is your R. This is your R. Now this is small signal. What is that? 1 sine 2 pi 60 t. Okay. So now it is a small signal analysis. Small signal model. So we replace diode with small signal model. This is small resistance. And what is the equation for RD, guys? RD, sub D. It was VT over I sub D. Okay, how much is it? The VT is 0.025 volt. And ID is 0.93 milliampere, which is 10 to the negative 3 ampere. So the unit is going to be ohm. So how much is it, guys? This calculate 0.025 over 0.93 times 10 to the negative 3 ampere.
It's like 26.88.
26.88. So approximately 26.9. Okay? So this is the small signal resistance. So that was step 1. This is basically step 2. Step 2. We now apply a small signal and we see small signal resistance is there. Now let's go back what we want. So calculate both DC voltage of the diode and amplitude of the sine wave signal appearing across here. So what is the voltage across it? So this voltage is going to be delta VD. Delta VD. Delta lowercase d lowercase d. So delta lowercase d as a function of time is going to be RD over R plus RD times V sub D. So using voltage division principle. Using voltage division principle, you get this. So now you just substitute the numbers. R is 26.9. How much was this uppercase R? 10 K. So it's 10 times 10 to the 3 plus 26.9 times 1 times sine 2 pi times 60 times t. So, can you give me this number, guys? 26.9 over 10,000 plus 26.9, you multiply by 1. What is this number?
Multiplying by the sign, right? That part?
Yeah, sign, we are going to keep it like that.
0.0026.
0 point 0.0027, and then sine 2 pi times 60 times t. Okay, so this is unit is going to be volt. So delta Vp t is going to be this. So in terms of millivolt, it is going to be 2.7 if you multiply by 1000, 2.7 sine 2 pi 60 times t. This is millivolt. Now if we graphically, if we plot Vd, so we have positive, negative. This is the resistance R, which is 10K. This is resistance R, which is 10K. And then if we have a diode, we get Vd as a function of time. And this is basically lowercase d uppercase s t, which is v plus you have 1 sine 2 pi 60 t. So this Vd is going to be, if you plot x-axis, y-axis. So this Vd is going to be 0.7 volt. 0.7 volt is going to be right here. So this is Vd. Now this is constant. 0.7 volt. Now what you do, you get a sinusoidal signal on top of it. So this is your total voltage V sub d t, and this amplitude is 2.7 millivolt. This amplitude is 2.7 millivolt. Okay, so this x-axis is time t, and y-axis is v sub d t, which is v sub dt. V sub dt means it is v sub capital D, which is the 0.7 volt, plus delta v d t. Okay, so that is the graphical representation of the output that we are expecting across the diode. Clear, guys? Crystal clear? All right. Now let's move on to next topic. Yeah, I just represented a small signal model here. I did that already in the solution. Now, small voltage regulation. The next topic is voltage regulation. So I'm not going to read my slide. So I'm just going to explain to you what we are going to talk about. This voltage regulation, diode has to be present to construct the circuit of a voltage regulator. So voltage regulation can be two types. One is in case the input voltage varies, output voltage is going to be constant. Regardless of the input voltage, output voltage is going to be constant. The other thing is, other type of voltage regulator is load variation, which means that the output voltage regulator, so that's voltage regulator. So the input voltage can vary, V in. The output voltage is going to be constant. Okay. Now, in case you apply, you have certain load, and all system people demonstrate with this load, because you can have many circuit here. In case you have certain load, and load can draw different current, I subtract. Load can draw different current. If load draws different current, regardless of the amount of current that load draws, no matter what, output voltage is going to be constant. So these are two types of disturbances countered by voltage. So load can vary, output voltage is going to be constant. Source can vary, but still output voltage is going to be constant. So voltage regulator circuit can be implemented in many different ways. So we are going to see the diode-based voltage regulation. So the diode-based voltage regulation shown to the circuit right here. Look. So after you apply some DC voltage here, guys. So let's say this DC voltage equals 10 volts here. So you apply 10 volt DC, okay? If you apply 10 volt DC, what is the output voltage here, guys? So you are taking the output from the anode terminal of diode D1, this is diode D2, this is diode D3. So the output you measure from the anode terminal of diode 1 and cathode terminal of diode 3. What will be the output? 0.7 volt in this diode, 0.7 volt in this diode, 0.7 volt for this diode. So what will be the total voltages? So you can think of this as 3 voltage sources connected in series. What will be the total?
7.9.
So it is going to be what?
It is 7.9.
Not 7. 0.7 plus 0.7 plus 0.7 is 2.1. It is the 2.1 volt. Now, if you put, let's say 100 volt right here, still output is going to be 2.1. Do you see that? BC voltage regulator. Doesn't matter if output is even 15 volt. You vary the voltage source, DC voltage source, your output voltage is going to remain the same because of the diode constant voltage source. Okay? But one condition here is that these diodes have to be forward biased, which means on. All the diodes have to be on. All the diodes have to be on. Not only that, they have to operate in exponential region. So you see the diode characteristics curve. Diode has to operate in exponential region, which means that high current should flow through the diode. If that is the case, we can simply design a voltage regulator using bunch of diodes connected in series. So based on this circuit, so you can read, for example, here it says current has to be, the diode has to operate in exponential region and current has to be greater than few microampere, and load current, as long as the current is greater than knee current is the current here. So this is called knee current. This is called knee current. This much current is called knee current, and this voltage is called knee voltage, which is 0.7 volt. So we go through a numerical example. Okay. In your version of slides, guys, I'm sure I will not the old version. It's a different example, right? It is example, it should be example 4.6. So I'm going to open the latest version of the slide. I'm sure. This is the example that we are talking about. So here, given the circuit to the right, with the power supply, here DC voltage is 10 volt. RL is 1K. Calculate the percentage change in the output regulated voltage delta. Delta VO percentage caused by a 10% change in the power supply voltage. So power supply voltage is going to be plus minus 10%. Power supply voltage is going to be changed by plus minus 10%, which means that it could be 11 volt or 9 volt. So this 10% is basically 1 volt change. 1 volt change. So in case your DC supply is changed by only 1 volt, what will be the percentage change, delta VO percentage change in the output? For 1 volt change in the input, what will be the percentage change in the output? So that is number one. And number two, when we connect 1 kilo ohm load here, then what will be the change in the output voltage? That's what it says. And we are going to assume constant voltage drop model with internal resistance or small signal resistance Vt over IT. So I'm not going to draw the circuit diagram in detail. By now you should know. By now we know from the previous example how to draw this. I'm not going to do this voltage source again. So I'm going to directly go through the solution. Here, solution DC biasing. DC biasing, your V plus is 10 volt. So we have V D1, V D2, V D3. So this is going to be 0.7 volt, 0.7 volt, and this is going to be V D2 is going to be 0.7 volt, and this is going to be 0.7 volt. So therefore here output voltage is going to be VD1 plus VD2 plus VD3 is going to be 0.7 plus 0.7 plus 0.7 equals 2.1. And the current flowing through this diode, because we did not connect the load yet, so the current flowing through this diode is going to be, you can think of this DC voltage, which is V plus equals 10 volt. We have one resistor connected in series. Now we have 3 diodes connected in series. So the current flowing through this 3 diode is ID, and this is R, and we know this voltage V out equals 2.1. So therefore, ID is simply using Ohm's law. ID is simply V plus minus V out over R, which is 10 minus 2.1 over, how much was R test?
10K. Or 1K.
This R.
Well, it's around though.
That's R. So it should be R actually. I forgot to substitute R. R should be 1K. So it is 1K, which is 1000. Could you please give me the calculation? That's 10 minus 2.1 over 1000. How much is it?
It's 7.9 million.
7.9 million, right? That is the current. So please do correct that this is R. Okay. So we did the DC biasing. Therefore, we know the output voltage across these 3 diodes, and we know the current flowing through this diode. Now, small signal model. Small signal model. What we do, small signal model, we have this small signal which is VDT, which is basically 1 volt. which is basically one volt. So 10% of VD. So now what we have here, we have one resistor R, and then we have for each diode we have one RD1, one small resistance, and for the second diode we have RD2, and for the third diode we have RD3. Okay, so this is going to be this is going to be VD over VT over ID. How much is it, guys? 0.025 over ID is 7.9 times 10 to the negative 3. How much is it? 3 point?
3.16.
So approximately 3.2. So you will have the same here, which is 3.2, and you will have the same thing here. So therefore, because of this small signal, the output that you are getting here, I call this delta VO. And this delta VO is going to be, using voltage division principle, delta VO is going to be VD over R plus 3 RD. That should be not VD. It is going to be R D1 plus R D2 plus R D3. Here you will have R D1 plus R D2 plus R D3. Basically the same thing. So here you have, so 3 times 3.2 over R is 1000 plus 3 times 3.2. How much is it, guys? 3 times 3.2 over 1000 plus 3 times 3.2.
Oh, it's like 9.5 millivolts.
9.5 millivolts. So look at that. We have in the input voltage we have 1 volt change, and the output voltage, how much is the change? 9.5 volt. 9.5 millivolt. So 1 volt change in the input changes 9.5 millivolt in the output. So the ideal output, ideally you have V out is 2.1 volt, but change delta VO is 9.5 millivolt. The percentage change is going to be VO is going to be 9.5 times 10 to the negative 3 over ideal voltage 2.1 times 100%. How much is it, guys? So percentage delta VO
We did multiply that.
yeah, we are multiplying by 100.
0.45. 0.45.
0.45, yeah, approximately that. So you can say that it's 0.5% approximately. And this is the final answer. This is the final answer. So you see 0.5% change in the output if you apply 1 volt change in the input. Okay, guys? Here? Okay, that's the main idea. I'm not going to solve the second part, so I will go through the second part, and I just have one topic to go over. I will spend half of the class next week to finish up chapter 4, and then we'll move on to BJT. We'll move on to transition. All right. So, who is now? Say, to make sure that I don't do the